So speaking of in theory, today's topic actually, I hope we more or less can cover two things, like the remaining LP, right, duality stuff that possibly could talk about, and so to finish with that, because that is interesting, and then again, so if I had to right now put that topic here, it would be linear programming and dualities, especially, like more of that, what's still missing. But in theory, like the main topic, we'll see what we get. And as I start right now with a commentary of the solution of yesterday's problem. I think it was D, the one about the game, the clearly game theory problem, the Sapinho's game. I think it was D, right? So I can say D. I never remember the letters. It's a difficulty. It's impossible. But by name or what are the about, I have more chances to remember it. Okay, so I will just right now more or less mention how it can be solved, like in the not necessarily well, a slightly hand wavy, but mostly like solution comes from heaven. Like how do you think about that way, and hopefully this will motivate that later with some heavy theory. This very specific. We don't often have problems using this kind of very specific theory, but there are a few, right, that it could appear. I have actually seen one recently that surprised me that something that kind appeared, but I guess you can reason in special case, but if you want to solve the theory, it might be easier. Okay, so for this one in particular, I don't know if everyone read the problem or was commenting the problem at least once. The main problem idea should be relatively simple. Like for a single ball, the game has a left player. They were actually green and brown in the statement of this particular problem, but let's use the terms left and right because they are standard. So let's get, if you go and read mathematical theory about game theory, these are the standard terms, right and left. And when we have to keep scores or count positions, which is something we will do, left is will be the positive player and right will be the negative. Right? This is also standard convention. Of course, this is convention, like the electricity, which is the negative charge convention. Right? This is arbitrary, but this is the standard. We'll see the score arrangement. So when we count a position and place a score to it, like this position is 3 moves in advantage to left, well, it will be +3. If it 3 moves in advantage to right, it will be -3. So in the case of this particular problem, the rule is that whoever plays chooses one of their control little triangles here, which were toads in the right, basically sapinhos or sapitos that jump, and push it forward. So that is the way the arrow shows. This would be a valid move in this case by the left player. Let's say left pushing things to the right because it is playing here on the left, and right is pushing here things on the left. Just say the only special rule is that when they are right together, the move is actually to jump, right? And you cannot leave that one, right? So you have many of these roles. And they are clearly independent in a way, but you're playing them all together, so in that sense they are not independent, but the set of moves is like a complete independent Cartesian product. Like what you do in one board will not affect the available moves in the others. Okay. So intuitively, the easiest case to more or less understand and think about in this one is what happens in any position. Well, I haven't mentioned it, but this is in this game, there was exactly one of these per row, right? That simplifies a lot of what kind of position we can make. We have many complete triangles. Everything is much more complicated. So okay, any position kind of like this, or let's make it a little bit more interesting like this. These are the easy cases because they cannot cross anymore. So it's actually easy to see that in any such position where they have already crossed, we can like split it right into two boards and actually think that they are independent now and have more rows, right? But these ones are very simple to understand. Like, okay, there are no moves available at all to left here, and right has two moves. You will jump once, and then you will jump again, right? So this position is clearly whenever right wants, they can do two moves at any point. Left can do nothing, right? The name of this situation is just +2. Right? That is how we call it. For I have an integer, well, a positive, let's say, number of moves available, and my opponent has no moves ever in this specific game by itself, which were left, right would very. Oh, sorry, I said this was right. Just because of the convention. This is the right player. So that's it. And this would be +1. In this game, there is one move available to left. So, of course, in very simple games like this, the negative ones, no matter who starts, right will win because they have moves at any time. And either at the very beginning or at the second turn, there are no moves for left, so left wins. Here it's exactly the opposite. So then, it is very intuitive. I hope that we can add this together without any problem. We have all of this. It works the same as -2 + 1, well, -2. There is a net one move advantage here for left. Sorry, for right. That here. Well, if with this intuition, if you have faith that you can somehow assign values to every position, well, there is some justification, but you can assign values to every position here, and you can start experimenting a lot with which those values are. So basically, you can draw from this idea and basically just count how many moves left has still available until the end. Like imagine that right did not exist, right? There was no collision. So here we would have like 3 moves, and right would have 1, 2, 3, 4 moves. This example, so it would be a -4. So that can give you, like, let's call it a delta, right? A count that if they actually passed through each other and did not interfere because of our analysis, this would basically be a -1. So let's call that, ignoring the collision number, the delta. Okay, that's just a definition for us. And what you can experiment and start discovering is, okay, the only thing that will matter is the delta of the position. So adding one free move at the end for each one will not change anything. That could prove, but you can intuit it that the difference is the only important thing. And how many, the distance, let's say, how far away they are until collision, right? So if the distance is negative, they have already crossed. Then the value, let's say, of the position is just the difference. We have like basically justified it like this. And then the magic part is what happens when it's not, right? So it ends up being the case that for d greater or equal than 0, it only depends on the parity. So I guess without using theory directly, you can discover all of this by experimentation, probably, like doing a lot of experiments. Perhaps a very good intuition, but I think you need to do a lot of experiments to start finding these things. So if this is even, or if this is odd, the behavior changes a little, right? Actually, it also depends on the value of delta. So we can do like a table here. So what happens if delta is 0? Delta is 1, or if it is lower, greater or equal than 2. Right? And for negative values, it will be the same, flipping the sign. Right? Those positions will give you an advantage for them. So, what is the solution? For the even case, it's actually that instead of just being delta, you basically get delta minus 1. For negative plus 1, it gets closer to 0. So a 1 delta advantage, this becomes no advantage, and this one will become delta minus 1. So this is also delta minus 1. If they still haven't crossed and the position is here. So one specific example of that will be something like this. Let's say something like this. Here, the delta count is like minus 1. It favors, no, it's plus 1. It favors left by 1. It has one more move if we count. So it looks like it should be a slight advantage for left. But if we actually, so in the normal situation, left has one move, so they always win, no matter who starts, because if it was only this position where the left starts and wins, and right has to play, they lose immediately. But here it's not the case. This one, whoever starts, loses. If left starts, they have to jump like this, and we get to a crossed situation, but right has one more move. Right will do. And if right starts, it is even more obvious that right will lose. It is a big disadvantage. So in this one, whoever starts loses, and that is more similar to the 0 situation where everything is balanced and whoever starts will run out of moves first than the other cases. So this one actually behaves like a 0. And because of that, everything has like one less. So you have and for odd difference in the middle, the distribution is given fine. This delta minus 1 remains. Here we have something similar to the 0, but I will call it star. Star is a value that you probably know if you did any game theory problem in your life. It is like the formal name for the heap of NIM of size 1. Right? And NIM is a game where any of the players can do the move and erase this. Right? So what we are saying is that a situation like this, where in the middle their distance is something odd, and the delta is exactly 1, so this will be the prototypical example, this little situation. This is completely equivalent, even though this game is not impartial, and there is a difference between them. This behaves exactly the same as the normal NIM heap of size 1, which is called star. And you can convince yourself by thinking about, okay, whoever starts gets the middle thing, and then they are together. And then it works as a 0, because one of the players cannot move, but if the other tries to move, it is immediately cancelled. It has no net effect. So it actually behaves like whoever plays first here can destroy the position. And that's all. And that is exactly the NIM heap, which is different from a total 0, which is we already know if you ever played, who knows the solution for NIM, which is like the classic game theory game most. That's good. We can do advanced things, otherwise we would have to go back to the basic. So you know that two NIM positions like that are a 0, so star has this very important problem that it adds back to 0. So if we have 2 of these, they cancel out. But if we have only 1 of these, like the star position, we know that whoever plays first wins if we see the holes. And this one is a very funny position, which you can get by experimentation. If you have something like this with a distance of 1, sorry, with a delta of 1, this total distance. So the same, but we can add, like, let's say, a slight advantage for left. They have a bit more room, so this can hurt them, but this is better, or equal. This situation, now if we check it, It's not like star, it's not like zero. Left always wins. In that sense, it is different, because if left starts, it becomes a symmetric situation, which is more or less easy to see. Whoever starts loses, so it is the zero situation. So it can move to zero. But if right moves first, left will do the same and still win. So left always wins in this one by itself, so it is better. But how much better? Well, if we compare to -1, like we play this, and we also play giving right one extra move. If you play this, if we play these two together correctly, right will win. So this is a slight advantage for left, but it is less than one move advantage. Because one move advantage for right is enough for right to always win in this combination. You can experiment. And I hope this intuition can make you, we will delve more into that in while I hope, at least a little bit. But the actual value of this is a half. Left has a half move advantage here. It's like a bit more. So it's half a move ahead. And a justification of that is that actually, if left has two of these positions, it is exactly the same as having something like this, like a real one move advantage. Like these two, in absolutely any combination of games, will ever behave exactly identical to this. So this justifies calling it a half. The half is exactly identical to exactly one move situation. So these are all the values. Once you have this, you add all of them together. If it is positive, left always wins. If it is negative, right always wins. If it is zero, it's us having the empty game, and that is whoever starts loses. And if it happens to be the star by itself, because if it is positive but with also a star, it changes nothing actually. It could just move on there, it's still positive or negative. If it is just a star, it is like the single ning heap, and in that specific situation, whoever plays first wins. Right? So that completes the whole analysis. Just complete values and add them all together with the rules and see what happens. Okay? If I tell you this table, you can actually, it's not hard to prove that it is correct. It's relatively simple to prove that this is correct once I reveal to you the solution. How would you prove it? Like, we won't do it in detail, but how would you prove it if you were forced to prove that this is correct and do a mathematical proof? Yes. In what sense? Like an exponential backtracking over some game for a mathematical proof.
See the result for one row.
But they want to prove that for any combination, it is the sum. I am saying that it is. Right? The basic idea is to use the standard. This is the key. Pn. Well, here it will be more complicated because it's who wins, right? But okay, whatever. For any position, I am saying that one of the players wins and the other loses. So basically by induction, right? Checking that for any position. If my calculation says the player to move has to lose, then you have to check that every move moves to a position that my same calculation says that the player to move has to win. Right? Because that means that whatever they do, it will change the situation, and by induction, it already works. And the other way around, if this calculation gives a position that whoever plays wins, you have to prove that in some of the boards of these values, there has to be a move that leads to a situation where the same calculation shows that the other one loses. Okay? So it's the analogous to n can always move to some p, it exists some, but from some p position, everything will lose. That same idea. Right? And by checking what the actual situation is, you know what moves you have. For example, from this one, if you advance, you reduce the distance, and it was positive because it is solved, so you will move to an even situation with one less delta. So from this one, you can actually move to this one. So you have some arrows of what you can do, and you can check carefully. So in a sense, it is sort of a good force of cases, but it's only like the final cases of the final result in the table. But that would be very tedious. But I mean, it would be possible to check it. But it's very hard to conjecture this, especially this is very hard to guess. You've never seen anything like this before. It's very unintuitive that half move advantages exist. It's very surprising. Okay, later we might mention more details, but this is just motivation for, okay, these kind of things exist, and that is why in game theory, when the players' move are not the same, which you will see, you will now notice that is a very unusual case. Most of the problems, especially in competitions, have the moves being exactly the same at all the time for both players. Well, the theory becomes from simple and nice to impossibly complicated, basically. When you lift that the restriction, they have different set of. Okay, any questions? Position, please.
I don't understand what means even.
Yes.
Zero. Why?
I mean, I did not explain any of this really. I just said this is true. So it's fair that you don't understand, but the 1/2 I just gave an intuition. I didn't prove this is equivalent to that. I just stated that it is true. But right now, I am not explaining anything greatly. So that is right. We can at least show an example. That would be so this one, the even. Well, actually, I have just done examples with 0 and 1. You have to trust, okay, only parity, and that's mattering, right? So 0 would be they are together, but they haven't crossed yet. That is why delta is 0. Well, this would be a minimum example, and that is an actual 0. There are no moves. So that minimal example is okay. That is the actual 0 game. No moves exist, right? So whoever starts can. But if you add 1 to each side, it will not change the fact that the one who starts will lose. Right? Here, if left starts, they get to a very bad position and the right place, and they lose. So this one still. We will see later in class that any position where whoever plays loses is equivalent to 0. So because of that general property, this will hold, basically. But yes, right now, a lot of this is, you might experimentally, with many cases, discover some pattern and guess it and send it, and it gives a correct answer. Okay? But it is much harder than knowing something. Okay, any other question? So this is not justified completely, but this is the solution. You could code it from this, just by magic. You say, okay, just using magic. Okay. With that said, let's now move to something totally different, which is LP. Let's try to finish the topics on linear programming that are still pending. And I think that it's not getting worse every day, but we are keeping like the same situation of the first day that, oh, okay, it needs a bit more time, and now every day is spilling to the next one. I hope it doesn't get completely worse, right? Let's see. But so far, I think it's remained constant. It's not growing, it's below. Okay. So what linear programming? There are a few things I wanted to mention. I mean, there are huge books written on this, so a lot could be said, but there are a few interesting things related to yesterday and the problems. So I would like to mention a bit. Okay. Oh, by the way, I forgot the running joke of this. This is my 5th favorite Monkey Island dish. It's actually true. Okay. So let's go to LP. A very important detail in general that I did not talk at all last lesson when we were solving problems with LP, right, with linear programming, and mentioning how to apply it, is caring about what is called feasibility, right? Whether there is a solution or not. A problem can be feasible if there is a solution, some solution, even if it's very bad, but some solution at all, or infeasible if there are 0 solutions, like the points in space that satisfy the restrictions is an empty set, right? That will be infeasible. I mean, infeasible, not. And it could be bounded or unbounded, basically. I mean, even if it is feasible, the solution can be bounded or it can be unbounded. It is nice to draw in 2D, right? So if you have, but for any dimension, it's the same idea. If you have a linear program, your restrictions might be something like, okay, it has to be to the right of this, below this, and above this. So this one is infeasible. If you try to find something that satisfies all of that, it's the empty set. Right? You have an intersection general algorithm should be able to be careful about this. Okay? So this can happen actually with a linear program. We only talk like assuming that it's always a solution, which many times is the case because of some situation the problem is well defined, so you don't have to worry about this in the particular example, but in the general case this can happen. And it can also be an unbounded problem. Let's say we only have these two first restrictions that I mentioned. So this generates an infinite region of feasibility in this specific example. And so, depending on the actual cost function, like what I am trying to, let's say, maximize, right, the goal function, this will be bounded. This now is feasible. There are infinite points here, a whole region of possible solutions, but I want the best one. So depending on how the vector looks, right, the goal function, there could be a single optimal solution. For example, if the vector is something like that, right, the C vector that I am trying to optimize the dot product of C with my coordinates x, y, okay, I would want the feasible point most in that direction, and just by looking at the drawing, in this case, there would be a single one. It is here, that would be the solution. That is the optimal point, and anything else is worse. But if this vector, in this same example, will have, let's say, down, simply just the goal function would be I want to minimize y coordinate. Right? Then just by the drawing, we see that this is an unbounded problem. Right? There is no optimal solution with a minimum I for any solution. There are things even with lower values, so that is what we mean by unbounded. Is that clear? So this is a general situation. You have to be careful. Actually, if we remember, we had weak duality. The weak duality theorem, right? The weak duality theorem said that if I see the value of some solution to the primary problem, right, it always will be lower or equal than the value of a solution to the dual problem, right? If I put a valid set of prices that is chosen so that it is always advantage to stop producing things and buy to me at these prices, what they will get from buying everything to me has to be greater than what they are getting producing, however they are producing the thing. It's very nice. And this is the weak duality theorem. So an important observation is that by the weak duality theorem, if, let's say I am thinking about my main problem and I go to the dual, and there is some solution in the dual, so the dual is feasible, there is any solution at all of the dual, by weak duality, I have a bound on my origin. Right? So there are some relations between both problems. We actually can do a simple table of the primal and the dual problem. For example, we can notice that if the dual, what I was just saying means that if the dual is, for example, feasible, so it is not, there would be like three cases. Unfeasible, feasible but unbounded, or precisely one nice solution, the good case. So if the dual is feasible, there is any solution at all, then the primal cannot be unbounded. It cannot be feasible but unbounded, because it does not make sense. Choose any solution, and by weak duality there is a bound. It cannot grow with it. Right? So there are some. There will be like 3 times 3 combinations, but many are forbidden. Just by this observation of the weak duality theorem, we see that only a few make sense, because basically the combination, this one is unbounded, which I will denote with infinite. Unbounded and feasible makes no sense, and the reverse, of course, also the same. The dual inequalities, basically. They are mutually dual to two work in this particular sense, right? They work for this. So they could be both infeasible, in principle. They could, in principle, be like problematic, both problematic, but for different reasons. But they cannot be both infinite, right? If both exist, then they mutually bound each other, so they are no longer unbounded, right? That combination would not make sense. But in principle, it could happen that one does not exist and the other exists and is well defined with a single solution. In principle, it does not violate weak duality, because weak duality in order to use it with one solution each. So here we don't have one solution each. Weak duality says nothing at all. It could be the other way around. It could also be the nice case, was the only one we are considering so far. We were considering so far that both exist. Okay, so this would be the table. Well, actually, we also saw that there is the strong duality theorem that says that this inequality holds here, basically. Well, actually, we were not too careful when we said that if problems are unfeasible, there's no equality to be able to hold here, but basically, what the actual statement of the strong duality theorem would say that if any of these exists, so if either in the dual or in the primal problem, there is one solution, the strong duality, which is true for linear programs, tells you that there will also be a solution in the other one, so they are both bounded, so both have a nice solution because they will actually achieve equality. So, because of strong duality, these two are impossible. So that leaves us with only. Is this the correct wording? Yes. So that leaves us with only these remaining 4 possibilities. Okay. Because we have strong duality. I want to strongly emphasize that strong duality only holds for linear programming with the reals, right? Weak duality is also true for integer linear programming, but strong duality, the equality and these nice results, is false for integer linear programming. Okay? If you limit yourself to the integers, you are restricting the solutions, and that could actually make the solution worse. It does not always match the same value that you can get in the reals if you restrict to the integers. And so, of course, once the value is not exactly the same because of this bound, the equality won't hold anymore. This nine, right? So if you are working in the integer case, you don't have strong duality. Only this kind of weak duality. Okay, which is reasonable because we know that integer linear programming is much harder. Okay. Any questions? Okay, so the other interesting thing of how to relate the primal and the dual, it's actually called complementary slackness. Right? Which I not managed to mention last class, but it might ask this question, like, okay, let's say I'm in the reals, I have strong duality. I happen to see that the dual is much more convenient, so I solve the dual. I do that, I have the optimal value, so I have the optimal value of my original problem. Everything looks great so far. But let's say that I have to reconstruct some working X vector. Right? This is now a very big problem because there is no bijection or direct relation at all. They even live in very different spaces, like this one the n dimension and this one dimension. There are examples like that. So it's not obvious at all how to convert this optimal solution you find for the dual into an actual optimal solution for the frame, right? And the way to do that is not very easy. In general, it might be easy, it might be hard, but the way is using what's called as complementary slackness. Right? Complementary slackness is an observation, basically. If we remember the proof that we had of weak quality, we had like the cost of the primer that is lower or equal than, well, this same thing plus the slack variables multiplied by the dual solution. So these slack variables were all the remaining stock, right? This is one solution that chooses how much to produce each product in the factory. It will satisfy the restriction, so for every restriction it has the sum of all the wood that I am doing lower or equal than the total wood that I have. So this difference, the total wood that I have in stock minus what I am actually using, which is given in this calculation, that subtraction is what I would call the slack variable I, which will always be greater or equal than 0, otherwise I was not satisfying the restriction. Correct, right? So this was clear because this is non-negative, right? Then we have many inequalities of calculation, and we reach C, B times Y, which is the value in the dual, minus the slack variables we were for the dual, which were the difference in price between producing the product and paying it at price E directly. It's the X, and this one is clearly lower than equal than B. This is how basically the proof looked of equality. We wrote that the other day. Well, if you look carefully, if you know that you are dealing with an optimal solution here and an optimal solution here, then all of these are equalities, a strong duality, which means that this has to be 0 and this has to be 0. Right? Because those are like the only places where there could be a gap, basically. This would mean, if this was not 0, it means, okay, at those prices, it was, you could get something better by redistributing and selling the excess stock, right? So this has to put, and this would be like, these prices are not minimum because I could reprice and avoid this difference, right? That is more like the intuition of the factory selling. That's for the calculation. So the observation is that if I have, for example, a solution, looking at this, if I already have, let's say, the optimal Y value, if I am looking for an optimal X value, actually, if I find any X value that satisfies both this and this, right? The V values will be fixed constants because they can be deduced, they only depend on Y. So if I have found an optimal Y, that implies the V values, and X is what I am searching for. So this would be many equations, right? The many equations that say this product, coordinate by coordinate, has to be 0. Otherwise, there is a gap, and I want no gap. I want to get the optimal. And this one is similar. Now, Y optimal will be the known constants, but this tells me something about the slack, which is the excellence resources that I will have in the origin. And since this is a dot product of non-negative things, basically what it says is that these additions of the product of two non-negative vectors, right, the dot product of non-negative vectors, they all have to be 0, so if the product of two things have to be 0, one of them has to be 0, right? So coordinate by coordinate in these two vectors, each of them have to be 0. So actually, what does it mean? That the way, this is if I manage to make it 0, the obtained X will be optimal. Right? So the observation is that if I solve the linear problem and get one Y optimal solution, I can write a linear system of equations, which is still like a matrix in general, but it is not a linear program. It is now a system of equations, right? I can solve with Gaussian elimination or with specific case solving. if I find a value of x that satisfies all of these equations, right, linear equations, it will be an optimal solution. That is now guaranteed by the same idea. And this is called complementary slackness, because if we actually look at what this means, because the product has to be zero, it basically says that, okay, for my optimal solution, anytime that I have a variable that I have used, let's call it that is positive, well, the corresponding slack variable in the primal must be zero for the product to become zero. So any variable that I use tells me that the matching restriction in the original was an equality. Right? So it becomes an equation I have to satisfy. And similarly, any slack variable that is zero in my solution of the dual, so any equation any slack variable that is positive, so any equation that has slack, any equation that when I look at it for the optimal Y solution is not an equality but has a slack, well, for the product to be zero, it means that it forces the corresponding I coordinate to zero. This one is nice. It's a very, we get also an equation, but it's extremely simple. It forces, okay, then in the primal this has to be a zero. For every equation that has slack in the dual in that particular solution, it forces, okay, in order to be optimal, it has to be a zero in the primal. The hard one is the other one. It's okay, and it will also tell you need to set to an equality this restriction, so they will be sort of the critical, right? You see it more or less. You can then check all the calculation, but the most important thing is that it turns finding x into a system of equations. Right? It might be hard because it might have an awful matrix, but it's easier than a linear problem. Right? We have achieved something. By solving the dual, if we need to recover x, well, all that is remaining due to complementary slackness is to solve as a normal system of equations, right? Not inequations, but equations. Okay? And the idea is also very nice due to duality. Positive variables in the solution become the critical restrictions in the original that you have to set for equality, and the other ones you can ignore. Those that happen to have 0 y in the solution, you can ignore those. And also for the equations in the dual, any equation that has slack that is not exactly at equality, you actually have to set the corresponding x to 0. Those are the conditions. Any questions? This is actually useful to reason and do the proof for what was problem D the other day about the cycle situation, right? Where in the primal problem, the original one, we have values in the edges and we need to set non-negative values in the nodes such that for every edge, the sum of the nodes is at least what it says, right? But the dual problem, becomes like, okay, place some numbers in the edges now, right? You have to place some numbers in the edges. Such that, well, now, okay, in order for the drawing to be nicer, it's still better to put it in the notes. So you still have the same drawing, but now in the notes you will have to put, no, my bad, you still have to put them in the edges because for each of these you have to put some number now, but the restriction is that for any two adjacent values, so if I choose x equals to 0.3 here, and I choose xy, and I choose xy plus 1 equal to 0.8, well, any neighbors have to add up to at most 1, right? Because originally I wanted to optimize the sum of my values, so all of those ones in the objective function, 1 x1 plus 1 x2 becomes the ones in the restriction. So this is a much nicer condition. All neighbors have to add up to 1 at most. And my goal functions ends up being Well, if I chose 0.3 of these elements, I get a value of 0.3 times 20. I want to maximize that. This is exactly the dual problem, okay? Which is much nicer to think. If all of the x were 0 or 1, so you either choose an element or not, and you cannot choose half an element or 2/3 an element, then it becomes immediately the nice combinatorial choose the maximum sum without two consecutive that we were mentioning. Right? So this is it. I don't know if you had checked that already, but that is how you get it. So if you solve this problem and you want to actually go back to the original, what would be the values in the original problem? The thing is that those places where you are using a non-zero quantity of that element, that tells you places where, in terms of the original values that you placed at those nodes, let's say this one was at 20, so I need to at least have a sum of 20. Well, this was if in the dual the optimal solution has a positive value here. In the original, this one was an equality. It is either 0.20, 1.19, 1.5, 18.5, but it has to be an equality. So it actually guides you to how to reconstruct. You check which ones are positive, and those are the equations that matter. The others you will not. And similarly, for your equations, anytime you have two consecutive that the numbers add up to 1, that the numbers do not add up to 1, that one has slack. So you know that the corresponding variable in the original you have to set to 0. Using those two things, you can reconstruct. And that is how I found the elementary proof that I didn't even mention, like you have to use Bellman 4, construct a graph, look at alternative paths. You can do an elementary proof of this property without going to the dual, which directly gives you, it has to be this number that you're looking. But it is hard to find. Well, the way to find that proof actually is by cheating and using complementary slackness and duality, and it tells you, okay, you will have to look at this equation. Those are the ones that matter. So that is how you do the magic step in the 3 process, and you actually know, oh, okay, I have to go and construct this out of nowhere solution because it was not that out of nowhere. By solving the dual complementary slackness, tell you, oh, these were the critical equations, right? The ones in the matching. I hope that helps relate a little bit more these two things, because some people were actually asking me about this, which is a reasonable question, like how you relate the solutions actually in the dual and the prime. That is much harder to see. Geometrically, they are so different, the two spaces, that it's hard to visualize. Okay, any questions? Good. Okay, and then the last duality thing I want to mention is that in many cases you have a special property that allows you to deduce that your problem, your original, let's say, problem in the reals, right, the linear problem, is actually an integral real problem, right? Which means that the solutions you are guaranteed to find it at integer values. So you can swap to the integer problem and it will be the same. Those cases are very nice, but that is not very common. But if the matrix, so just to recap, we know that a linear program looks like this, and I want to maximize this will be the factory canonical example. Well, it was a maximization one. I want to maximize C times X. Okay? So if I go to the dual problem, I can solve. Well, if the matrix A has certain nice properties, then I am guaranteed that for any B and any C that I choose, as long as they are integer, there will be an optimal solution to this in the integer. So the problem is like it remains at the integer, right? The condition on the matrix is that it is what is called unimodular, which is a very theoretical condition. Basically means that if you look at the matrix and do any the determinant of any submatrix, so that means if erasing any rows and erasing any columns, you can actually you get a square matrix and you do the determinant of that, well, if all of those possible determinants can only be 0, 1, or -1, right? They are one of those. Then the matrix is called totally unimodular. In that case, you are guaranteed to have 9%. The idea of this is because of Kramer's rule, basically. If you solve a linear system, there is a formula that is called Kramer's rules that the actual solution for some coordinate is exactly the determinant of the original matrix with some replacement of a column that you have to do, but this will be integer if the matrix is an integer, and it's in the numerator. The critical part, which is the denominator, is always, well, let's call it M, right? This might not be the same thing. It's the matrix of the linear system you happen to be solving. So the denominator is the determinant. So a corollary of this is that if you have an integer matrix that has determinant 1, Kramer's rule tells you, okay, the solutions are always at integers, right? Because the formula only divides by 1. And for -1, it will be this. For 0, well, the formula breaks, but that sub-matrix was singular. It can give nice solutions. Okay? There is an extremely good, by the way, 3 blue, 1 brown video on this, on the Kramer's rule, so very recommended. But this is a famous formula, and that is the reason of why this happens. Well, when you do the precise calculation of where the optimal will be, because of convexity, it will be at some vertex, right, of the complicated polytope. So where can the vertices be? They have to be at some intersection of restrictions. So there will be some sub-matrix somewhere that has the critical restriction, right, and the critical variables that will actually tell you what you need to satisfy to find the vertex. And in that critical calculation, you have a square matrix that, by Kramer's rule, this will be the formula. So as long as all square matrix, right, all sub-matrices, I emphasize, you can delete any column or any rows, right, not necessarily consecutive. That's the usual linear algebra notion of sub-matrix. You can delete anyone. If all of them are 1, 0, -1, well, you are guaranteed to get integers because I have no clue which matrix will be the critical one, but they all have integer value. Okay, is that clear? Actually, what we usually do is that we know some well-known cases where the matrices are well known to be strictly unimodular. It's good to know a few of those. You can go to Wikipedia and there are many more examples. I have around here the most important ones, I think they are. One is the incidence matrix of bipartite graph. So what does this mean? If A looks like you have a bipartite graph and variables in the nodes, and all of the restrictions are like the sum of these two something, right? That happens to be an A that is totally good. If the graph is bipartite, otherwise it is not. That is very well known result. And this is what's behind conic theorem, if you know that, and that's why it only works for bipartite graphs, and actually the dual of max independent set ends up being, once everything is linear, because it is if it is bipartite, now we know, the dual of max independent set becomes minimum vertex cover, which happen to be the same in the bipartite by conic theorem. Well, again, it is a specific case of dual. This one is a very well known. Are very well known, good to know. Is the flow network matrix, right? Or the circulation network. The other day I showed the example of circulation and how that one happened to, the dual happened to be like the continuous version of min cat. Well, that matrix is well known to be totally unimodular, so it happens to be the case that then the continuous solution of the continuous min cat problem is actually realized at the discrete version, so it was the min cat. No surprise, we already knew min flow min cat holds, but everything fits together. Right? It's good that it is fitting. Another interesting one is if your matrix happens to be like at every row has zeros and consecutive ones somewhere. So all of the restrictions are the sum of a consecutive set of variables by index, something, right? Any such system, these matrices are also totally unimodular. So even if your numbers are real, if your variables are real, the optimum is always at integer. That's also very common. And this actually allows you to use the dual problem in the tree problem, which is a very hard IOI problem. And the dual is a very interesting problem that looks very different. In my impression, they are both hard and similar, right? But a few things were more intuitive to me in the dual than others, but when I finally analyzed everything, like I was thinking mainly in the dual, but in the end I went back, oh, this is easier to explain in the original. And they are quite similar. But not the same, so it's interesting to have like two ways of thinking, even though in that particular case, it's not like it makes the problem much easier, but it's interesting. Okay. So this one was in one of the contests, so that you have the reference of what problem I am talking about, you will notice it. And this is very good. And then of course there are many simple transformations on a matrix that you can do and will keep this. Like you can transpose and it will keep being totally unimodular. You can duplicate rows or columns and it will keep being like that. You can multiply by -1 and it will be, right? Actually the dual of this one you might involve copying columns and multiplying by -1, but that just preserves the situation. Okay. These I think are the most well known. There are other examples. But these ones are good to know. Okay. Yes.
In this case of this segment of
Yes.
non-zero coefficients.
Not non-zero, but 0 or 1. Much stronger. Yes. If you put arbitrary numbers here, it can give arbitrary data.
To the width of the segment. Must be the same for all the.
No, they can be any I and j where it starts. Like it goes from I to j, which is arbitrary they are completely arbitrary intervals. So the restrictions would look like the sum of variables xy plus x, so a range sum basically of the variables. This was an array, this is sub-array simply. And depending if the problem was in our canonical form, they were lower or both at the same time, because by swapping the signs, they could all be -1, that is okay. Because again, multiplying by -1 will not. But not arbitrary numbers like 10 times this variable, that gives you almost a general metric. Okay. Good. And actually, the very final note is that from this observation of the Kramer rule, well, these are the well-known cases where the determinants cannot be anything other than -1, 0, or 1. But if you happen to have a matrix that is extremely close to this, but there's like a little detail separate, like, I don't know, a graph that is almost bipartite because it is actually a single cycle, but the cycle happens to be odd. So it's one edge away, whatever I remove, it becomes a path, and paths are bipartite, so paths with duality holds immediately, right? If you're very, very close, you might check, and your determinants might be very controlled. If you do the matrix for the cycle, the matrix would look like 1, 1, and 0. 0, 1, 0, sorry, 1, 0. Let's do one of size 5. Something like this. And the very last row, it wraps around. So any row or column that I remove, I am removing at least a node, so it will become a path. So those are already part of the totally unimodular long path. So the only one that could break is the full maze. Right? And if you do the determinant of this, which is easy to do because there are many zeros, so just this times this is easy to do, it will be 2. Perhaps -2 depending on how I put the order, but either one of them. So this immediately tells you by the same proof, if you understand the reason and do not just copy Wikipedia, okay, that in the dual of this, and the primal too, all your values have denominator at most 2. So the optimal is either an integer or half integer. Right? And you know that for free, let's say, because of, well, the night, by knowing these results. But that helps a lot with solving the dual, because now it is really a fully combinatorial nice problem. Like it's the maximum without two consecutive sum, but instead of picking an element, you can like half pick it. So you get half the value, and the restriction is that the sum of the consecutives cannot be more than one. So if you only choose 0 or 1 is the normal one, but if you choose half of an element, well, you are allowed to choose half of the neighbor, and that works. So if you look at that carefully, the only case when using any half value makes sense if you use half values for all of the variables. You look around, because otherwise you will hit a 0 somewhere, and you can see that this is not optimal, because either the odd or the even ones will be better than that. So immediately you have, oh, okay, it's the nice solution, or everything a half. You have fully solved the problem very quickly, but using heavy machinery for that, right? But taking all of this as known theory, the actual solution of the problem is very short. Okay, let's go to the dual. Oh, the matrix actually has 2 as the only possibility. So solutions of the dual are at half integers. Oh, looking at them, if there is some half value, but not everything is half value, it will look like this. And locally, I can either set the odd ones to 1 and the others to 0, or vice versa. And because they have the same sums, one of the largest one of those is better than everything at the half. So the only significant solution that the half point adds to me is if everything in the cycle is a half, so at that specific solution. So I think that this is a very nice application. Okay. Now I have fully completed all the material I had about everything. Any questions? There is, of course, a lot more to read about this. Mathematicians study a lot of this, but I think around here is the limit of what I can imagine being used in a context. Like more heavy machinery, I doubt if you would ever use it. Okay, I think we are done. We could go slightly early. Okay, let's do coffee break now, and in 20 minutes we do game theory.
sea, cada vez que sobreescribo
Let's move on. And for the rest of today, let's see a bit of game theory. For those of you who don't know, I really like. So you have to stop me. If I talk too much about game theory. No, not today. I mean, like instead. In this class, it probably makes sense. It's the game theory. Yes, like there are very advanced topics and very niche. I guess today we can do a bit more advanced than usual for competitive programming class. But there's way more advanced stuff that, I mean, something like the Sapinius problem that we mentioned with partisan games is already quite unusual. I have seen very few real problems involving something like that, so going to much more advanced than that does not make much sense probably, but it is extremely easy. If you happen to like these topics, I will encourage you to actually look for, well, there is like the Bible of combinatorial game theory, which you might have heard about, which is a book called Winning Ways. You will just find it by that name because there are not many things called Winning Ways. But the full name is Winning Ways for your mathematical plays. It's huge, I think. There was a paper edition that is like 4 books of this size, something like that, and it's completely huge. But a lot of that is like specific example of games. Like, okay, let's study this game, and they start doing a lot of calculation, and okay, the optimal way to play this particular game is like this. Awesome, move on, another game, right? But a lot of that is general theory. A lot of theory, but a lot of combination. So we will cover some things that are there. I mean, all of the combinatorial game theory there, unless extremely new things, but I think most open problems that are mentioned here must still be open. It's like P versus MP. It's very hard to advance, right? There are very few things that have been solved. Okay, so actually, first of all, I know that you know basic game theory. We have already mentioned that for us, games will usually be, in general, like in the most general setting, can be seen as graphs of positions and moves, and we move from one position to another. And we almost always will have graphs without cycles, so that we are guaranteed that the game will finish at some point, right? And we already know the very key rule that if you can make a move such that in that position, you already knew that, well, you're giving the turn to your opponent, so your opponent plays, and if in that position he does not have a winning strategy but you, then immediately you can bring back that winning strategy that you had here when it was not your turn to here when it is your turn. And other than that, you lose. That is the most key property. We have used that, we know that already. I asked before, but let's recap because I think there's more people than when I asked at the beginning. How many of you already know how to solve, let's say, impartial games, right? When you have the sum of many games, and you can use NIM theory, right? And compute the values and solve the game. Okay, it's similar to what I remember before. It's most, but a few don't know. Okay, it's right in between. Okay, we might be doing very advanced stuff, but we will probably quickly mention this again, right? But you can read this in the classical part, and for the most part, I will assume you probably know that. Still, we might want to mention some elementary classic ideas first, because of how useful they are. One of them would be strategy stealing argument, but we saw that already, so I just want to recap that because of how useful it is. Whenever you have some situation in a classic impartial game, right, where you have a position that you dominate in a sense of moves, like from your original one you can move to any position that this other one can, then your original one is winning, and the other ones you have no. It's a nice, non-constructive, right? Remember, that was because if this one is losing, I win immediately. If not, it is winning. It has some losing position here as an option.
I have that tools in both cases there. That's a very nice act.
And this was useful for the everything NIM problem, mind you, right? In that one, you can actually, so that was one of the problems that we had. I don't remember which letter, but you had many numbers, many heaps of stones, and the rule is that the player to move can subtract the same positive number from all of them, but they cannot go ever to negatives, right? And the ones that become 0, for example, if now I subtract 2, it will become 0, 3, 5, 5, 8, 6, and this one disappears. So it won't stop me from now subtracting more. But in this first step, I can subtract at most 2, because nothing can become negative. So who wins? And in this one, although it's not necessary because we could actually think of a fully constructive solution and understand the problem, to me it is easier to do it like something in between and use strategy stealing to help, because by strategy stealing you can deduce that if the smallest number is anything greater or equal than 2, the position is immediately first player wins, right? Simply because strategy stealing. You have the option to subtracting all minus 1. Let's say that this could be bigger. In this case, if I subtract all the smallest one minus 1, I can get something like this. This is my reference position, and this is the option. And well, from this one, the only legal move, actually, it's easy to do the drawing. The only legal move is to subtract 1. And it will become a 0 that will disappear, and the other ones subtract 1. But this position is, of course, an option that was already available in the original game. So this is the situation. It's strategy stealing, it's a win. I don't know the strategy because it depends on whether this one is winning or not, but without computing that, we know any position where the minimum is larger than 2 or larger is immediately winning. And that simplifies a lot the rest of the problem, right? In the end, what matters is whether, if you look at the number from the start or not, are 1, 2, 3, 4, 5. So it is an easy, and the critical part is which is the first one that is missing. So it's not too hard to guess and find patterns, but if you notice this, you very quickly get to that. I think it helps a lot because, okay, unless it has a 1, everything is solved. And if it has a 1, there is only one legal move, so I look one step forward. If there isn't a 1, the same. So immediately you get this pattern. Right? It's like immediate strategy. Did you solve it like this, or some did, the others like more doubtful? Okay, good. That's awesome. So I found this is a nice example of applying strategies. Okay. So we do a few little things that I want to mention of games without doing the sum of game, and then we move directly to the sum of game, which is the most theoretical and interesting part of combinatorial game theory. Actually, we could attach, we are only doing combinatorial game theory. It's good to notice, if you haven't done that before, if you Google for game theory, you'll likely find a lot of theory about the case when you have games of imperfect information and you have strategies and a matrix of options and Nash equilibrium. Well, that is still game theory, but it's not the part that we use here, which is combinatorial game theory. That is like the name by which we will find it. And it's very useful in economics, that one, and that is why it is more famous, perhaps. And if you Google it just as game theory, you will find a lot of material about the other one, but we are using combinatorial game theory. All of these books about this, about combinatorial. Okay, one very famous game, which still has many open questions around it, just like run this game, is a width of game. So I will mention this one as an example of something I want to show. So this is one specific known game, right? Let's use it as practice and warm-up before we move to more complicated things. In width of game, we have basically the typical story that you have a queen in the single basic width of game. You have a chess queen on the board. So it is a piece that moves in diagonals and horizontally and vertically. But in this case, it is restricted to move much simpler. Upwards, any number of moves. To the left, any numbers of cells. Or diagonally, like subtracting 1 to both coordinates, or 2 to both coordinates, and so on. If it were here, well, it would have 1, 2 options to the left, 1, 2, 3 options above, 1, 2 options in diagonal, right? That is the valid move. And from this position 0, 0, let's say, if you put coordinates into it, you cannot move. And the rule is that whoever cannot move loses, right? So we want to compute the n positions and the p position, right, for this game. So how do we do that? To compute the n position and the p position. The recipe is always the same. For the terminal positions, you check the rules of the game. Here it is the normal rule, so terminals are p positions. They could be n positions if the rule were like who cannot place queens, which is unusual but can appear something. But then the non-base case, that one always has the same pattern. If I check all my options and there is some pre-position, I can win because I move there and the other player loses. If not, any move I do, I go to a situation where the next player will win, so I am forced to lose. So for every position, I can just check, okay, I check all the options, this has a P, so this is N. I check all the options, so this has a P, this is N. And so on. For this one, I would do the same. I check all the options, right? Here I would check. This is one option, this is one option, this is one option. One of those is a losing position, a P position. The previous player to play wins, so this one is an N position. And for example, here, I would check the 3 options, and all of the options are N, so this one is N. And so on. Right? Do you see that this would be the standard, let's say, way to solve this? That way, if someone asks me what is the result of the width of game if the queen starts, I have no clue. This is probably pronounced width of, I guess. I don't know. Let's say width of, but I don't know how to pronounce. If I am at a certain position, I just check the letter that I compute in this matrix, and that will tell me. Right? So what is the complexity of doing this calculation? Let's say for an n times n matrix. Right? Let's keep it simpler and say that this is a square. If it's not, it's basically the same. Just so that I have n everywhere, and I have to think less. What would be the complexity of this? Right? Right, because I have n squared cells, right? But each of those involve a 4 visiting n other squares. Right? So this is cubic time to fill the matrix. This would be the standard way to compute this. Can we do better? Right, we can do order square, that would be nice. How do we do it?
With an array saying that if there's a P in this row or this column, and we go filling like row major order, that tells us if there's a P, and also the
I see, so it would require some bookkeeping, like if I did not understood incorrectly, you would represent it something like, okay, this row happens to have a P at position 0, let's say column 0. This one has a 1 at position 2. Is this what you mean? Something
like I mean, if this row has a P or not.
Okay, only the Boolean extension. And why is that helpful?
Because when you visit position, you check if the row has a P, if the column has a P, or the diagonal has a P.
Oh, I see. Okay.
By the order you fill it, you're guaranteed to visit the values.
Right. Okay, that makes sense. That will work. Do you see it? Right? It's basically an optimization over the direct recursion, right? Which is a very normal way to solve problems, by the way. So it is very reasonable that that's what you're thinking. It is very common, this pattern, that so this actually looks quite similar to prefix sum. We could literally do it with prefix sum. We will want to count whether there are or aren't p positions. So we could actually imagine that p positions are ones because we want to find them and count them, and the other ones are zero. So then I would like to have some prefix sum over the column to quickly query the sum of a column or a prefix of a column so that I know if there is a p position and avoid the for, and the same for rows and diagonals. That would be a standard technique. I think it's equivalent to the Boolean. The Boolean stores even less, right? But this is more general perhaps. So very classic technique, I would get n squared. That makes sense. So I would like you to notice that there is like a more general pattern that is very often useful in game theory problems like this, especially because of the pattern of how usually p positions arises. So in some games it might not help at all, but in many games it makes sense to do it this way. And I call it, I have quite arbitrarily called it the sieve trick. Actually, I call it el truco de la criba in Spanish, but I'm not sure how you say this in Portuguese at all. But in English, it will be the sieve trick. I think this is the first time I see it written in English. What is the sieve trick? Well, I mean the sieve of the primes, right? What is the algorithm for computing prime number? I guess you want to have the primes up to number n. You all know how to efficiently compute that. Right. Just as a recap, there is an extremely efficient, like, it will end up being order n log n time. Doesn't matter why right now, just do the calculation. It's the final complexity, so almost linear, very fast. Which is known as the sieve algorithm. Let's put two letters, p, which means the number is prime, nothing to do with previous player to play, and n, that means it is not prime, so nothing to do with, nothing to do at all with this is the next player to play that will win. And the algorithm says, okay, so one is not prime, this is like a base case, right? Very special case, I could even start with two if it is confusing. And then I say, oh, okay, initially everything might be prime. That's basically how the algorithm works. And then I go in increasing order because I am going to skip multiples. And the idea is, okay, what is a prime number? Is one that has no divisors. But it is very hard to, for a number, check the divisor. There is no pattern. That is a very general coding pattern, especially in problems, that if I want to look at the divisors, and I can pre-compute or do things in a different order, it is often the case that I want to look at the multiples instead and do everything the other way around. Because checking multiples is so much more convenient than checking divisors. For multiples, there is a very simple pattern. The multiples of x are x, x plus x, x plus x plus x. So I can keep adding and go through all the multiples while going directly to the divisors is very hard. It's basically equivalent to factoring for given a single number, right? And that is a hard problem. So with this idea, I go the other way around, from numbers to multiples. And actually, because a prime is a number without multiples, the idea that I guess Eratosthenes invented millennia ago was, okay, 2 is prime, for sure. So now I go to all the multiples and they have it as a divisor, so you can already erase them, or let's not erase them, let's just say they are not primes, so let's put an n there. And we keep going as far as we need, right? Here I am computing only up to 10. And then, okay, 2 is done. I move to the next one. It says p, so it hasn't been discarded, so it has to be prime, because if it was not prime, it would have a divisor, and when I check that divisor, because it was to the left, I skip the multiples, I would have checked it already. Okay? And that is the idea. For every prime, I check the multiples. This ends up being very fast, mainly because there are few primes. The reason why this ends up being this complexity is basically that there is a theorem that there are only about n divided by log n primes from 1 to n. Right? This is a very good theorem. And this is the reason why you integrate this and you get this function. It's basically, you do the summation and you get this. It's no mystery, it's just this is approximately how many primes there are. Because there are few primes, the complexity is much better. That's the intuition. So you keep skipping, right? The thing is, this is actually a game theory algorithm. Eratosthenes did not know it yet. But this is a general algorithm to compute the P and N positions, right? The winning, losing position for any impartial game like this, right? You go in topological sort order of the DAG, so that you go, when you get to a position, you have already processed all its options before, and you do the same idea. Because the pattern is exactly the same. From a P position, you could actually invent, I leave that to you as an exercise. You can invent an extremely boring game and easy to play where it's very obvious that you will lose if you are at a prime and win if you are not at a prime, but a formally well-defined game, and this is computing the winning positions of the game. So actually computing prime. But in general, if you have a P position, well, anything that can move to it is N. So we can do the same idea. Go the other way around, and when we see a P position, we mark as N. Possibly it was already marked as N, but doesn't matter. I process it and mark as N any predecessor, let's say, anything that can move to it, the transpose graph. Okay? And if I keep doing it, when I arrive at a position, if it's N, it can be skipped, right? Because for the purposes of calculation, checking its predecessors is useless, because if I did it from the other way, I would say, oh, this is an N, useless, skip it. So I check it the other way. All of the transition will be useless, there will be nothing to do. So N positions, no need to check the predecessors. Doesn't mean anything. The important thing is P positions are the ones that cause the predecessors to be N. Right? Do you see the pattern? It's exactly the same. So this is a general idea. It's an alternative way to compute the same dynamic programming algorithm, right? Some people, the general idea in dynamic programming was reversing the arrows for the calculation, computing the same value, but the order of computation being changed so that children modify the value of the parents, call it something push DP, there are other names maybe. It would be an example of that idea. But it is very common that it helps in theory problems, because it is very common that there be very few P positions. That is basically the idea. If we carefully look at the complexity of this, like in general, push DP has the same complexity as direct normal DP. It doesn't change because you check each transition once. That is the main idea. So it's the same graph, everything is the same. But here we have the detail that in this pattern, in this game theory pattern, it's like in the sieve of Eratosthenes. It is helping the complexity. It would be helping the complexity. It depends on the shape of the particular game. Because you skip the N positions. So you could say that the normal dynamic programming complexity is sum over all P positions, X, let's say, over any position in the game, right? I don't know, let's say the degree of X, how expensive it is to compute X, right? And this adds up to the whole graph, right? Let's just very informally say the size of the whole graph of movements, right? But for this version, the actual cost that we're paying is the sum over only the P positions of the size of the reverse, let's say, right? Because it's going the other way, as here, of that P position. Which, well, of course, it is at most the size of the whole graph, but it might be smaller because you're at least skipping something, right? I would have to add the number of nodes at least once because they have to at least be skipped and at least be initialized, but maybe I can skip all the edges. And this is the case here, right? If I have to do it by hand, it is obvious that it is a better algorithm because it is much more convenient. This P causes everything that is a predecessor to become N. So I very quickly fill a lot of the table. Right? When I go in row major order, I can skip a lot P position. Okay, now I have to settle the preceding node. These are like the multiples, these are prime numbers. That's all of them. I keep going. I found another one that is still initially all would be P position. I set them to N position. So I do the same here. So by hand it is much more convenient. It's already clear. I keep going, and I think I find this one. I probably might. Oh no, this is because this is not square. Okay, that's the reason. So this is a P position, and this one would be 2. Right? To make it square. Okay. And there I would have found all of the P positions in this particular example. There doesn't seem to be any here. I think
Should be the left.
maybe I did a mistake, but I feel it should be like this.
The last.
This one is here, yes. Is it? Yeah, it was similar. That's what happens. Yeah, this one makes this. Okay, thank you. That's what happens when you add a row on the flag. Okay. So what is the complexity of this? It is actually n squared. Like you see, because the detailed complexity would be, okay, how many p positions I have, those are the ones that pay the, in this case, linear cost of checking the options, because one way or the other, here it is always linear. And then there's a fixed quadratic cost of, okay, iterating the table. But this, in this case, adds up to quadratic because there are at most n p positions. Right? That is easy to see because in this game, there is at most one p position per row. It is inconsistent to have two p positions in the same row because from the right one you can move to the left one, then it would not be a position. Is this clear? So I think this is much easier to do than the other option of bookkeeping some prefix sum or some boolean of adding, like, do not add more things, just do for, but the other way and set everything. Okay. So it's good to know that it can help in many games. It is a general pattern because in many games, the exception is like the p position. The planets have to align for a position to be looked like. Generally, things are winning. When you have many options, that's the case because it's easy like to move to the specific one. Of course, it depends on each game. There are games that maybe all the even positions are losing, and all the opposite ones are winning, and then they're in a sense half and half. Right? But like the general typical, if things look more or less random, is that there are many n positions and few people. That's why this is good. Right? Okay. Any question about this? Have you used this pattern before in game for game theory purposes?
This is exactly the problem already happening in Brazilian competition.
Oh, I see.
It's
Nice.
marbles. It's about a lot of marbles that you can move like that, and you need to say who you win.
Oh, but you have many of those.
Yeah. So you
Okay, then you cannot use this trick because you want the number. You would have, I mean, it's not obvious how to avoid the but the setting makes sense. Yes, I see. So that's a good point. If we have a sum of game, for those of you that know NIM, we would like to know the Grandi numbers, right? The max values, and this only computes whether it's winning or losing, so whether the Grandi number is 0 or not. It is not computing the detailed Grandi numbers. For that one, this very nice trick would not be usable. Right? We might need some very efficient data structure for that. Cannot avoid the complication. Yes.
Could you calculate this just in ON without making all the n squared?
I am not aware of any way. Like the general pattern of the p positions for this game, like to have a nice characterization, I think is an open problem.
Well, like,
I'm pretty sure. Maybe there is linear time because it's not so bad linear time. That might exist, but like a formula, I think is open problem.
it's not like a formula, but in each column you have only one p.
Okay, yes, you know there will be one, so you keep the index of the first
Okay,
one.
yeah,
And at
you
some
have
point
two
it will
range.
appear.
The range of the p that you
No, makes sense.
and the range of the p in
Right, they
45 degrees.
might be like points in 2D or 3D, right? Because you have to know like the row
Yeah, you
and
have
the diagonal, right? Which is like another coordinate. Yeah, that's probably at least n log n something there. Yeah, that makes sense. It's not a formula, but yeah.
There's a formula.
I think that makes sense. Quickly judging it, I think it works. Might be missing something, but yes. So we now have another input problem to set up. Yes.
There is actually a formula for this game.
There is a formula.
Yeah.
Oh, then I am mistaken, man. You sure?
Yeah, you can check it on Wikipedia. I think there's a nice explanation.
Then it had to be that there is no formula for the max values.
Yeah, the max
Okay.
values I don't know, but just
Okay, I
for P and N
misremembered.
positions, it's
Then
nice.
thank you. So what is still open then, thanks for the correction, is the detail of the Grandi numbers, right? So if you had to do a sum of this game, that one is hard. But the P position, then there is a formula. Okay, good to know. I misremembered that. Any other questions?
The main point is that the P are in these lines. So
You mean for the formula?
no.
Ah, for an algorithm.
No, for the formula. It's
Okay.
these two lines like that. And I think you can like do some computation to get some approximations. I think it's the main idea about the formula.
Okay. Good to know. I did not know that one, but it's interesting. So I misremembered, but it was the next value. Thank you. Okay, any other questions? Okay, good. So this trick is very common, and often it is as easy to code as the direct DP, like this, when the direct and the reverse transition are basically the same as is here. It's almost the same code, but it can speed up. Good to know. Also, noticing this pattern is very helpful if you are doing tables by hand to look at the pattern while your teammate is doing something on the computer and you don't have the computer. It's the same as we saw experimentally. It's much faster to fill the values, right? With this idea of moving to the end position to just fill them, right? So it's also good if you're looking at patterns by hand. Okay. So it's one very nice idea. Let's move on. Then another, so this first part, I want to mention a few tricks, basically, which you might not know. I think that it's not particularly hard at all, but it is not very common to see, so perhaps you haven't seen it before. I might call it loopy games, just to invent a name to it. I think I saw this name somewhere. I think I remember this name, so it sounds fun. So let's use it. But it's basically what happens if the game graph has cycles. I mean, in principle, now the game could be infinite. So we need to define what's going on, right? We need to be precise, okay, what does it mean if there are cycles? Because usually the games are guaranteed to terminate because they are cycles, so they are progressing. And so it's easier to define what's going on. We actually know, we have already mentioned that we have like the determinacy theorem, which is all positions are N or P. There is like no third option. Someone has a winning strategy because the game is progressing. So by induction, recursively, you can compute and assign the actual strategies, right, by the basic rules. So you have some P position as an option, you are winning. Otherwise, your position is lost, right? If there are cycles, well, it's much less clear. The usual definition of what happens, I mean, basically we can still define the notion of playing the game. Playing the game is we are standing at some position of the game, and the move, whoever has the move, is to move the character, right, as usual. And the only difference is that, okay, the game might not terminate, right? I mean, if it does terminate and get to a terminal position, the rules of the game must already say whether this is P or N, like the normal rule. It is actually called like that. The normal rule is that you cannot play, you lose. But it is allowed that the base case, I mean, the game could at least say, this position is N by the rules, right? That is allowed. At least for the basic. But the new possibility is that maybe the players start playing, right? And the game goes on forever. That suddenly becomes a possibility. Might be harder to reason about because infinities are always hard to reason about, but mathematically it makes sense. Like if every player picks a strategy, which would be a tree of possibilities of what to do in every position and whatever way, or anything equivalent to that, you can face two strategies and see what happens, and a new thing that can happen is the game goes on forever. And they keep moving through the graph and never get to the terminal. So the usual definition is that it's like triple repetition in chess. If any of you play chess, I mean, something looks forever, okay, it's a tie. Right? So suddenly there are ties. That's a usual convention. Let's just assume. I feel like that is the most natural. Right? I mean, the other option would be to say, the word exploded and the game is broken, something like that. And if you have to put a result, I mean, nobody would have won. So a tie is like the most. So with that convention, you can actually adapt the rules a little bit and compute whether each position is previous player has a winning strategy, next player has a winning strategy, or neither, which is a new possibility. Neither has a winning strategy. which means that if they both play optimally, they will actually tie. The game will look. Because if it does not, somebody made a mistake, right? Because by definition, not having a winning strategy means that there is no such way to force the other one to do so. Well, it might be subtle. There is some subtleties in what is the final winner, but it is actually the case that either one player wins, the other wins, or both can force the game to live forever or win, right? Something favorable. So the actual result for optimal play is that. At least as long as the comparison is like everyone prefers to win, and if not, prefers to die, and the worst thing is to win. So how does it change the rules? Actually, for the terminal positions, that's direct. And our very basic formulas are still correct. Like if I can move to a B position, it means that the previous player to place has a winning strategy. Oh, that's me. I am the previous player to place. So here I have a winning strategy explicitly. I can give it. My strategy is move there and use the strategy. Right? Action that way. So this rule still works. The other one, when I have already labeled all of my options, right? If I have already labeled all of my options, and they are all n actually, there are no undefined options. This one allows undefined options. Yeah, it doesn't matter. I have one winning move. That's enough. No, don't need more winning moves. This other rule is there is no winning move. I have already labeled all of the options, and they are all n. Well, this one still holds. I am a P position, like this position is lost. The strategy for my opponent is let me do one move. Whatever I do, they will have to win it. So these two still hold. So the idea is use those two as much as you can. Basically, computationally, you would want to keep track of the out degree of nodes, but when you complete a node, you subtract to the out degree of the predecessors because the out degree will be counting the number of edges going to incomplete nodes, basically. So when something reaches 0, it becomes a node that can be solved because it has a mysterious option. So you would do that, and you would also use the rule that, okay, any P position that you see, you can immediately label the predecessors as n. Right? By combining both things, you can solve many games, even if they have loops. Right? Like this. Can I do anything else? I think now I cannot apply the rules anymore. I am not in a position to apply anything. Can I? Sorry? But this one has a... right, you're right. Yes, thank you. This one, all of my options are labeled, and it is an n, so I am unavoidably lost. Great, and that, I think, breaks the cycle, because here I have a P position, this is n. This one now can only move to n position, so this is P. And this one can move to P position, so this is n. So in this case, there is a winning strategy, right? I mean, the game could loop forever here. It is a legal game to keep looping. But now we know that they are playing very badly. Someone has winning strategies at some point, and they are not using it. Okay? Here it is quite clear that when it is your turn and you are here, you can win immediately, right? You are not. It's like you don't want to win, for example. Do you see? Is it clear? Okay. And actually, I don't know. Let's modify this example a little bit. We were in this situation, right? And let's imagine that we cannot make progress at some moment. So this one, I don't know, we have an option like here. For example, something like that. Now, I think we cannot make any more progress. Let's check. This one I cannot label, my only option is mysterious. This one, I cannot label, my options, I have unsolved options and no preposition. This one, mystery. This one, I have unsolved options and no prepositions to complete, so yes, I cannot complete anything more. So, what do we do now? What do you expect that happens once you cannot apply the rules anymore, and this is like the maximal values you can feel?
You can still do stealing, right?
Here,
Like
to try to apply strategy stealing.
yeah, not in this example.
Okay, that's interesting. Let's see the general strategy stealing. It will look like this, right? It means something like this. Well, you cannot use I think you can use strategy stealing to justify that you will not lose. But now you cannot deduce that you will win. The outcome might be a tie. So yes, we need to adapt a bit because now it is not true that the solutions are win or lose. The tie is now an option. And that is a good point. You can adapt strategy stealing and it still works, but the conclusion is no longer I win, is I cannot be a P position. Because if I am a P position, whatever I do, they all have to be N positions. And this one does not make sense. All of its options go to N position, it should have been P position. Right? But you could be a tie, that is not discounted. Okay? So that's an interesting observation. The actual algorithm is, well, once you block, the algorithm cannot progress, everything that remains is a tie. And you can actually prove it, or just remember it and believe it. But you can prove it because the strategy is quite simple. If you are in a tie position, make sure that you don't leave the tie positions unless you win. That's all you need to do. So here, do not move here because you are losing if you do. If you move outside of the ties, it has to be to win, to go to a P position. So for example, your opponent left you here, okay, move to the P position immediately. They made a mistake, something like that. Right? Actually, you won't ever have the option, if you currently are in a tie position, you won't ever have the option to move to a P position. Right? This is wrong. This had to be an N position. It was not blocked yet. Okay, so that will not happen. When the first player to leave the tie component, let's say, there might be many components, but whichever they are playing, will certainly move to an N position. So the first one to leave the cycles loses. So nobody will lose. That is fairly intuitive. But we can deduce this only once we have properly labeled things and we are not blocked anymore. Okay? This is clear. So it's actually no big deal. It's very similar to a normal algorithm. At some point, you cannot progress anymore, and the remaining ones are ties. Okay? Any questions? There might be some other crazy rules for what happens in a loopy game, but this is the most normal one, and the one I know. Just saying, okay, it is a tie, and it is an intermediate result between those two, right? Usually, there is some monotonicity, like if you say that in case of ties, some players win, then I'm pretty sure that you can basically collapse all of the ties to that player wins. If there were scores or something more complicated, this might become sort of undefined, but I mean, that should not happen. Okay. So no question about loopy games when the graph is not that. This is the last time that the graph will have cycles. Yes?
Can you deal with some loopy games?
Sorry?
With some, like...
Oh, okay, that's an excellent question. You can. The main idea is that instead of computing only P and N values, you compute the max. So this will be a 0 position, this one can move only 0, so it behaves as an int pile of 1. This one can move to 0 or 1, so it behaves like an int pile of 2. And now you cannot progress it, right? Basically, you can, if you know about NIM theory, the way to fill the values that every node is the minimum excluded number from the options, right? So this matches our experience. If my options are all already numbered and there is no 0, 0 is the first one excluded and 0 is like the P position. So it matches the normal rule for this. If all of them are labeled and no P position, I am a P position, right? And related to that, if some position is 0, well, I don't know the number, but for sure it is not 0, right? So it is for the traditional one. So you can basically compute the numbers like here. For the rest, you won't be able to compute numbers directly. But I don't know. I don't know of any standard notation for this, so I just invent infinite. You can put values that are like infinite or tie or special value. This will loop, but you keep track of what options you have in terms of Grandi numbers. Okay, this is a loopy game, but you have the option to collapse it to number 2 if you want. Right? that is, you could move to a nim heap of 2. By itself, that's a bad idea because you lose. But if there is another nim heap of 2 lying around, this might be a great idea because in total, this is 2 plus 2, which is 0, because these are nim heaps which are combined in XOR, so that becomes a winning move. So basically, you keep track of what options you have that have labels. So here you also would have the 2, and this one has no option to a move. Is it correct when I say yes? I think so. This should be infinite. And if I am not mistaken, the basic situation that you will find is that if you add 2 infinite values anywhere, you become the infinite with empty set, let's say. This I did not write anything, so this will be empty set. So these things below should be set. Right? You have many options, like you can move to 3 and to 8. Your value is, I'm an infinite that can move to 2, to 3, and to 8. Right? You keep track of all your options. You need to, because those are the nim heaps that, if they were lying out there, would help you win immediately. Right? Those are precisely the ones you could win the game if they were lying right there. So basically, if you add up any 2 of these, it is a tie, right? Because the first, it's like if someone at some point reduces the sum to only 1 infinite component, it's either still a tie or they have made a terrible mistake and they lose. So, once you have 2 infinites, it will be a tie for sure. But if you have only 1, you have to check whether your options allow you to win, basically. And and in terms of summing values, it just means that if you have a certain set and you sum it not with an infinite but with an actual value, where all of the values in the set are XORed with that. That would be the computational. Yeah, I think I've never seen a problem that uses sum of looping games, but this would be like the way to do it. And it ends up having a relatively simple description still. I have seen very few problems that have looping games and you have to compute win, tie, lose. That is slightly more complex.
So every element?
Every element, yeah. So this is like this, an infinite that can move to 3, 5, and 8. And you are adding, apart from this, I have a nim heap of 2. Right, I mean, you could move to 3, but then it would actually be 3 XOR with 2, so it makes sense that your actual move was to 3 XOR 2, which is 1, and so on for each option. Right, so that's why it's sort of, you can build it in already in the value. Okay. This I've never seen a problem involving this, but this would be the rule. But you can check it by checking that it satisfies the sum, the full rule for the sum that I'm giving satisfies the basic rule that if I say you are in a P position, you only can move to N. If I say you are in an N position, you for sure can move to P position. And that is enough, because then the rest must be time, right? Because of the original algorithm, right? Only that we will be looking at it in the graph of the sum of the games. Not explicitly, but implicitly. So that's an interesting question. I've never seen a problem using it, but now you have the tools to invent it in the local context. So good luck. Any question? Other question about looping games, please?
I didn't understand why the 2 infinites sometimes.
Basically, each player has a strategy that allows them not to lose. That will be. What is the strategy? Is basically to keep the infinites going. Right? Every infinite position has an option to keep an infinite. That's because of how they were built. If they only had finite options, you could compute a value. So the player just keeps the infinite there and they are not losing until, for them to lose, the opponent has to at some point reduce the sum, which might have many infinites, to only one actual infinite and then many concrete numbers. And once that happens, then it is your turn and there is only one infinite. So you can actually check, can I move to an actual 0 now and win? If you can, then you do it, and your strategy is even better. Your opponent made a mistake and you win. And if not, you still can move, and moving will always change the values. So if now you had an option to move to 0, you move to something that has not an option to move to 0, and that will always keep going. Okay. That might be slightly tricky, but I will leave it as an exercise. The thing is, the strategy, all you have to do is do not keep moving in the infinites until there is only one, and once there is only one, the rule is win if you can immediately, otherwise keep moving in the infinite. I mean, you might keep moving in the infinites and make sure to move to an infinite that does not contain a 0, right? Because an infinite that contains a 0 allows the player to move to 0 and win. These are the infinite that the set might be bigger, but infinites that contain a 0 are exactly the ones that by itself become n position. Become n position. So you have to make sure to not move to one of that. And you will always have an option. You cannot have only option to move to this one.
Sorry.
I think.
By definition, the infinites can't have a 0. The zeros are in position.
You're right. You're right. This means so this would have to be an actual, let's say, infinite that moves to a 2. But when I add another real 2 somewhere, the sum behaves like an infinite that can't move to a 0. Right? Like not in the real local specific graph, but in the sum now it can happen. So in that sense, these are the infinite. So yeah, that's a tricky thing. So yes, it involves some reasoning why it is the rule, but it is the rule.
So an infinite that can't move to a 0 becomes just a pi.
If you compute the final values and that is the result, yes. The only infinite, once you are in an infinite position, you either win because you can immediately, or it will be a tie. There are no losing infinites, let's say. In the final, in this sense, right? Because of the final. Well, in the other one, in the single gaming sense, there aren't 2 because in the single game case, all of the infinites are tied. But even in this case. Okay.
Yes. What happens with the upper left infinite?
This one is like if it is somewhere, things will be a tie. Like this one by itself, once you put it in a sum, force is a tie because it has no option. It's a bit tricky to see why, but once you have this and you lose, you made a mistake. If you have this plus more things that you are adding together, like this one here gives you a recipe of how to loop the game forever, just by this being here. So if you end up losing, you made a mistake. You had a recipe for not losing and you did. So, and both the players end up having that strategy. And the strategy is again to keep the infinites unless you can win immediately, but the fact that this one had no way to move means that you won't win immediately. It is a bit tricky to see because there are like 2 senses of what the values mean. Like a single graph case that we are mentioning, and then things like infinite with a 0 do not exist. But then if we start adding up many of those with the rule, these things can appear, and then it means, oh, this is actually many infinites, but the rule of how to win involves not leaving the infinite, or leaving them at the exact time, right? But anyway, this is like the rule of what to do. I leave it as an exercise to think of the details, because it is a bit tricky, yes. I mean, I haven't seen ever a problem involving the sum of the loopy games like this, but this will be the recipe. I mean, it's easy to remember that adding to infinity it's a tie. You can break. Okay, any other? Okay, that's all I have about loopy games. Okay, so for what remains today, and I guess we keep about the same length of spillover, like we're consistently, it's not getting worse, but we're consistently spilling over from the first day, every class and it will be next. So maybe I mention a few more things tomorrow, again, together with the final filler tricks and extra topics.
So for what's remaining today, let's move to actual combinatorial games and the sum games. So we'll study combinatorial games and the sum games. Up to now, we were not mentioning the sum of games.
Well, we did just a moment ago because you asked. It was not my intention, but most of the lesson was about only P and N values. But combinatorial game theory is concerned mainly with the idea of the addition of games, right? I guess you all know by this point what the addition of game is. Well, perhaps a few, not many of you do because you mentioned the NIM. You even know the NIM solution. But if you have many games, like I don't know, I have a width of game like the one before where the queen is here. And I also have a NIM heap of 3 stones, let's say, right? For those who don't know, a NIM is the game where you have many heaps of stones, and the rule is extremely simple. Your allowed move is to choose one pile, one heap, and subtract from it a positive number of stones, right? That's it. And the normal game is that whoever cannot move loses, and keep doing that. Well, if you have NIM with a single pile, well, it's very easy. This game by itself, you erase everything and win. But you might consider the sum of game. And that creates a new game, and it is just playing both at the same time. That is the whole idea. What does it mean exactly to play both at the same time? Well, you have one of them, you have one of the other, you put them both at the same time on a bigger table, right, of the game, to make a game. I cannot draw it because first I have to do this together. Okay. You have a very badly shaped table, right? But you put both boards on the table, and that is the rule. Okay. You go, you choose a game, and you move. And you go around. Now the other player comes. Okay. So you are literally playing both at the same time. So none of the games is yours, in a sense, right? You can choose any and make one move. So, and again, whoever cannot move loses, okay? That is one important thing to mention. The normal rule, I have said it many times, the normal rule is if you have no move at all anywhere, you lose. There is something called, well, the other case, the misère rule, which is literally misery in French. I have no clue why it is in French. It is the standard. The misère rule is the other one, the not normal one. If you don't have a move, you win. And this is not like a simple flip of booleans or anything like that. This one has extremely nice, well, at least, let's say, much easier theory in comparison. This one is completely impossible. This is intractable on so many levels. Like the general case of this rule for the sum is impossible. Extremely intractable. Much harder. So we will never talk about this one at all. You might look up the specific strategy for misère NIM, which is easy. That is a pattern. There are many specific games where playing the misère version of the game, where if you cannot move, you win. Is like do the normal strategy and then at some critical step flip a bit and you solve it. But that's like special case. Like the general case, there are many games that are completely untractable. So know that this case in general is extremely hard. This case in general, well, you can build a lot of useful things. Do not get confused by that. So we will only deal with the normal rule, and of course we want to be able to know who wins, as usual, right? So in a sense, like the goal of combinatorial game theory, let's say like the holy grail of combinatorial game theory, the final objective that will, if we achieve it, is like, okay, we actually did our mission, we did what we wanted to do, we are doing combinatorial game theory, is to be able to do the following. How big is the graph of the sum of two games? Like to us, usually implicitly, like you usually do not want to, well, sometimes if the game is actually played on a graph that is here, well, it is explicit. But usually
the graph of the game is something very explicit. You have either a table of positions or a situation where pieces are on a board, and it is all implicit. Right? But you have some graph of the game, right? So now we have two or more because you can sum with this concept. It is clear that this is commutative and associative. Like it is just put them all out there and you play. The new game is bigger and the move is choose one and play there. So it's just like union of collections, right? Like multi-sets. It's clearly associative. All of them is proper. But the new game, if you wanted to build the graph and count the states, it is clearly huge, right? It are clear to all of you. Like there is a combinatorial explosion here. Like if this one has n nodes, n1 nodes, and this one has 2 nodes, if I want to do any kind of general, like how would I create the game of the graph of the sum in general so that it always works, it clearly would need the product, right? n1 times n2 nodes. Because every node would, in the sum will have to encode, I mean, I can write it literally. It is which node I am in the first game and which node I am in the second game, right? It is not unlike the intersection automaton that Andrew mentioned, but it's quite similar. There are specific cases where you might have exactly one automaton, perhaps, but it's very similar idea. It's a kind of Cartesian product. You say where I am in the first game, where I am in the second. And if I have many games, of course, you start multiplying the states, and it's exponentially huge, the graph. So in general, I can't build the whole graph, right? That's very clear. So the idea, the holy grail, the objective that we want to do in combinatorial game theory is we would like to be able to do magic here and do some computations and say, okay, each of these nodes has some magic value or whatever. I do some computation that is at least polynomial in this graph, let's say, right? And then I do the same on this one separately. And if the sum has more terms, the same. Like for each one individually, do something reasonable that is not exponentially huge. And then at the end, I have like the summary value for each one, and to efficiently do a combination and know what happens with the sum. Right? Is that clear? That is like the general idea of all combinatorial game theory, to be able to do those kind of things. There is no such, even for impartial games. So right now I will mention that there are two kinds of games: impartial games, combinatorial games, partisan or partial, depending on where you find games, which is basically the other ones, right? So impartial is like the special case, and this will be no restriction. General games. It's like the real numbers and the complex numbers. Well, the real are complex too. It's like now so in impartial games, which are most of, I think all of the ones we mentioned, except the introductory opinions, which I showed the solution without detailed justifications at all. The by far most common case to find is the impartial case, where at every position, so at every node in the graph, both players have the same set of options. Like the moves are symmetric. The rule says, from this position, this is what you can do. And they never say like in chess, you know, if you are player white, then you can only move pieces white. If you are player black, you can only move pieces black. Right? That it does not exist. If we have an impartial sum of many chess positions, then each position there is some player that has the turn. So when it is my turn, I go and I move somewhere, right? And maybe that would mean that I play many times in the same board consecutively because my opponent is playing in another one. So here I play as black, and then when I come again, I play as white, and then as black. Is that clear? That could happen in an impartial game. But if I'm doing a partisan sum, there is a distinction, and the rules of the game might say which moves a player can do. So if I do a partisan sum of many copies of the game of chess, then the actual rule is like, okay, I have to move, but I can only make one of my legal moves in one of the games. So now each player has a role. One plays, let's say, white piece, and the other the blue piece. Do you see that the sum of games becomes very different in those two cases. Like, it has a different meaning, even for what. This is important because for a single game, it doesn't matter that much the distinction between partial and impartial game, because if you're only playing one game, there is like a parity argument. Like on every odd turn, let's say white will play, and on every even turn, black will play. So you could think that the rules are actually symmetric, right? Like the game includes a light that tells you whose turn it is. It might be the chess clock. And the actual rule is, okay, you come to the board, you look whose turn it is, and you make a move with that play. If you are playing a single game, it is exactly the same as the actual normal game, where you are playing a single player. You only move white or you only move black because parity forces. Right? But summing many of those games is very different from doing a sum where you are actually restricted. You only move your piece. Okay, some of you got it. And so actually, when we model games as graphs like this, we are already doing only the impartial case, right? Because for the partial case, we would need like two graphs. What are the moves that let's call it the left player is allowed to do? So if I encode it by blue just in this drawing, the standard terminology is that one player is called left and the other is called right, just to distinguish them, as if they were playing one on the left and on the right. So from this position, maybe left is allowed to go here and but this we do not want because we want the game to always finish. So it still cannot have a cycle anywhere, right? It cannot allow for back and forth. That would be too uncontrollable. But maybe both can move here, but blue cannot move here, right? So now it's like two independent situations. From any position, there are the moves that are allowed for left player, and there are the moves that are allowed for right player. So these are more complicated. Okay? That would be a partisan game. So the most common case is impartial games, right? Where we only, formally, we still have the two colors if we want, but they always coincide. So we focus only on each other. Okay? Is that clear? Okay. So for impartial games, we actually have a very well-known that you will find in, now, for example, I'm pretty sure it is mentioned at some place in some versions of the Guide to Competitive Programming. There are some old top tutorials that are good at mentioning it. There are countless Codeforces blog. I'm sure if you look for how to sum of games, it will mention how to do this. And many of you already know it, but for the impartial case, we have a general theory. That is the nice thing. We can actually achieve this ideal that we have of being able to analyze each game separately, compute something, and then efficiently combine them, and we will know what to do in the sum. In that case, you have to compute what is called as the Grandi numbers, right? Because there is a very powerful theorem that for impartial games, when your game does not distinguish between left and right, both players have the, and also recursively, like in the whole graph of the game, like every position leads to a situation where always the rule is that whoever plays has the same set of moves. There is no asymmetry, no distinction. In those games which are impartial, each of those is actually equivalent in the sense that we will precise a little bit. To a sum, to a single name heap, which is very surprising. So this graph just has to be completely equivalent, and in my mind I can replace it with a single name heap that behaves identically, even though it might not look like it that, of a certain number. So this would be what is called as star 5. So star is the notation for the name heaps, which in impartial games is all that there is, so the star might look somewhat redundant, like okay, why say star 1, star 2, star 0 is the same as 0, basically, that's notation. Why put a star everywhere since you only have name heaps? Just write the number. Well, in the general case, you have much more complicated kind of games, and 5 is not the same as star 5. And you also have -5. Right? We have already seen this when we analyzed the Sapinius example to game stamming intuition. For partial games, a game like 5 is like the Sapinho's position, where the left player, which we will by convention always say that is the positive one, so positive position favor left. In this one, left has 5 moves available at any time to do in a row, to try to do the last move, right? It's good to have moves in reserve, while right has nothing. This would mean the 5. And -5 is the opposite. It's a position where right has 5 moves available. While the nim heap of 5 is very different. That one is like neutral. Any of them can move and subtract. So it's a completely different thing, right? But when we are dealing with impartial games, none of these crazy new things exist. All that we have is nim positions. And the rule ends up being very nice and very mechanical. The recipe is actually, for each node, you just compute the max, as we were mentioning before. So terminal positions always get zeros, and then for each position that has already been solved all the options, you check the minimum number that does not appear. So for this one, 0 and 2 are the options, 1 does not appear, so this one will be our. The intuition for that is, I want this to behave as a nim heap of size x, so I need to be able to subtract, and I have the options by max definition to all of the values that are lower than x. So that makes sense. If I want it to behave as a pile of heap of size x, I can. And if my opponent tries to make it more complicated and grows the position, well, it cannot move to an exactly x position. It will have to grow, otherwise the max is wrong. Well, if they do that, I immediately reverse it, because by definition of the max, I can do that. So that is the gist of why this is actually equivalent. It does behave like that. This is the strategic way to make it behave like that. So whoever has a winning strategy, if this is a real nim heap, does this. They pretend it is, and if the opponent happens to do the new exotic moves, those are immediately reversible to a situation with the same x. So by induction, this strategy is okay. That is very quickly the next proof of the Grandly theorem, that everything impartial behaves exactly like an nim heap. Right? So this one would be a 0. Right? Losing positions are exactly the 0. Okay, and the actual rule is that to combine, when you have the sum of many nim heaps, well, that one you can discover by studying the game of nim specifically and what is the winning strategy. And the winning strategy is basically to always leave a XOR of 0. That you can, once you guess that, you can check by the typical property, right? If you are at XOR of 0, you have to modify something, so you will move to XOR non-zero, everything is working. If your XOR is non-zero, you can check the most significant digit in binary, right, of the XOR. Find some number that has that set as 1, so now you reduce it, and now you flip the other one as however you wish, and you are reducing some flip, and you can make the XOR 0. So that's the constructive proof of how to win. So, since everything is equivalent to nim, and in nim it works like that you have to XOR, in general you have to XOR. So that is the actual sum theorem for impartial game. So we are done. This is the full theory for impartial games. You do this computation, which is linear time in the graph. It matches our goal. Do something efficient in each graph separately, no explosion of multiplication. And then the combination is just the XOR. Right? The XOR is the way to do the combination. This was a quick recap. Unfortunately, the full theory of partisan games is very complicated. And there is no such thing as always working efficient way to achieve this ideal situation, that you analyze each game separately, you get some values, you combine them, perhaps with XOR. Well, we know that it contains XOR as a very special case, right? And now, because we have seen basic Sapinho's positions like this, right? We know that it contains the integers, right? So it obviously contains the combination. We have things like 5 plus star 3. It makes sense. I mean, I am playing a position where the left player has advantage. They can do 5 moves and the opponent cannot do anything, right? But also a nim heap of size 3. You can play that sum. Everything makes sense, right? And you can ask yourself, okay, in that situation, if they play, who will win? This one is very obvious. There is a lot of advantage to the left player, no matter who starts actually. left player will win. If they start, they erase everything, the opponent has no move, they win. If right starts, well, they can only reduce the hit, but then the situation is basically the same, and they will lose. Because this is too big of an advantage, right? So this gives an intuition that values can start becoming very, very complicated. Okay? But in general, there is no such solution. The problem of given many graphs like this, tell me, and I'm doing the addition, but these are not impartial games. I basically give you two graphs if you want, right? With each edge will be labeled either left or right to tell you who is allowed to do that, right? That would describe a partial game or a partisan game. A general problem is MP hard, and it's very, very hard. I think it might be, I'm pretty sure it is actually p-space hard, which is worse. I mean, for us, it's basically the same. You cannot solve it. But it makes sense that you cannot even check the answer. If I tell you, okay, left wins, what proof can I give you? Like, you have to do the full search trick, right? For Hamiltonian path, I can quickly show you the path. Here, I cannot even, I couldn't even hold the checker, right? We all solved it the problem. For Hamiltonian or something like that, there is a simple checker. You give me a path, I check it. Here, there's not even a way to check. But still, there is no general case. So what we can do is analyzing some specific common case and try to solve those. Any question? This is the general setting and a very fast recap of the classic theory. If you didn't know it, now you know how to solve any impartial game, which is very important. There are still a lot of, most of the problems are about that, about impartial games. For the less complicated ones, you will have a lot of time to absorb. But just once more, you complete the max, then you XOR, right? And if the XOR is non-zero, it was a winning position. If it is a zero, it is a losing position. That is the fully efficient case for impartial games. For partial games, everything is quite much more complex. But we can at least give some special cases. Right? I might mention a few more tomorrow, but one such special case is the case of what is called numbers. Right? So let's just mention this one quickly. And from how complicated this very specific but common example is, you will start to see that the general theory of this explodes, right? But there are many common patterns. So there is a certain subset of partisan games, right, which are called numbers, which intuitively are games where any move that you make worsens your position, right? We already know one very basic example, which is, let's say the integers, right? A position where right can never move, is not allowed to move, and left has the option to do a certain number of moves, that is a positive integer. The notation makes a lot of sense because you can actually check that if you have one move advantage and the other player has one move advantage and you have both boards at the same time, this behaves exactly like a zero. Okay? Tomorrow I might formalize it a little more, or perhaps not. I will choose what to do tomorrow. I think I will complete this. But those values we already know. Okay. So, intuitively, making a move worsens your position in both cases. You see that I have 5 available moves. Let's say I am the left player, the one that positive is good. I have 5 available moves. If someone forced me to play there, well, my only option is to move to 4 available moves. And it is extremely intuitive that 5 is greater than 4. This is worse for me. I prefer to have 5. Right? I have clearly worsened my position. No matter what the other games are, if in the starting position I change a game where I have 4 moves to a game where I have 5 moves available just for me, this one is clearly better. In that sense, making a move here, it also gives the turn to the opponent, so it changes things. But if who has the turn had not changed, I would always prefer having 5 moves and not 4 for sure. Right? So in that sense, these moves worsen your position.
So numbers are intuitively games where every single move that you can make worsens your position. And that makes things more controlled.
In general, games where moving is good and you want to move become much more complicated.
Right? As a general rule. I will just mention the rule as a motivation. Doing the full proofs will be probably too long and not necessary. But because of this intuition that numbers are positions where any move worsens your position, there is a standard notation for games that we can use, which is to write what are my options as a set. So for an impartial game, let's say an in heap of size 3, I could just write a single set. What are my valid moves? So I would write 0, which is the same as star 0, it's an empty game, nothing to do. Star, which is the standard name for star 1, the single heap of 1 stone. Star 2, that's it, right? From a heap of size 3, you can subtract and move to any lower heap, right? So this would be like the abstract notation of how a game like this is formed. Just think of it as a set of what are its moves. It's an equivalent way to think of a graph. I would say every node is actually the set of its options. That is quite convenient when doing things on paper. But this is only for impartial games, because for partisan games, the sets of options might differ. A bit more complicated. So the way we write it is that in general we write the left options here, and this is where the name left comes from. It's written on the left. And we put the right options. And this is like the abstract set notation of what a game is. It's just a pair of two sets. The set of what games can I leave to my opponent if I am left and I make a move in this position, and what games can I leave my opponent if I am right and I make a move in this position. Right? So by this notation, the empty game is just written like this, two empty sets. Right? This is sort of an abuse of notation, but it is the standard way to notate this, right? Empty set here, empty set here, right? If I put nothing, it is empty. So this is the actual 0 game, which obviously does not alter anything in the sum, because nobody can play there. That's why it's called like that. And we can actually use games that we already know to create new games. This would be akin to creating the graph node by node and seeing what we can actually get, right? So with this notation, familiar. 1, the game where I have only one move advantage, was like this. For example, this one already cannot move, but right still has one move. And that's all that can be done yet. This would be 1 as a game. Well, in the abstract notation, left player, if I am identifying that left player is here and moves to the right in this particular game, is a positive one. Left has the option to move to 0, to the game where everything has finished. So left has this option, but right cannot move at all. Right? So this is the way it looks abstractly to have one move advantage. Left has one move advantage because left can move to the 0 position and finish. Right has no move. They do not have the right to move. It is clear what this notation means. Okay. Similarly, 2 would look like this. Left can move to the situation where there is only one move, and right still has no right to move. Okay? If it is clear. I haven't defined the equivalence of game, but we have been using it intuitively, and if you have done problems, as most of you have with impartial games, you already have a good intuition of what game equivalence is. Two games are equivalent if swapping them in a sum of games will never change the result. So that is what allows us to actually simplify this. We have many partial games, I know that I can simplify all of that, and the sum of all of those behave in any sum of games as if it just were the final XOR as a single input. Well, in that sense, we can still define with that same idea the equivalence of two games when they will never change the result of any sum.
even for the partisan case. But checking equivalence, well, it becomes much harder, and the actual values grow out of control. They become an extremely complex sea of possibilities. For example, I don't know if you see it intuitively, but if I add a worse option to the player left, for example, and create a game like this, this will be equivalent to the original. It makes a lot of intuitive sense, but I don't know if everyone sees it. So in game theory, we would write this is equal. Since equivalent is the most important thing, like the equal sign is used for the game equivalence and not for the these graphs are identical or intuitive equal operator. Occasionally the 3 lines are used for that. But most of the time we only care about the values. So this game and this game are completely equivalent. Right? The intuition is that if you have the option to move to a position where you have 1 move left, and you have the option to move to a position where you have 0 move left and the game finished, but it's pretty obvious that you want to move always to this one. This is a pattern that the programming will use a lot. This is called a dominated option. So 0 is a dominated option here because 1 is bigger. Here it is literally bigger as long as we have numbers. It's just checking that the number is bigger. And for right, it would be the other way around. If left has 2 options, but 1 is bigger, left will always prefer the bigger. And if right has many options, but 1 is smaller, right wants the negative values, right? Right will always prefer the small. So that is a way to justify that these two end up being the same. This is quite loosely, but you can formally prove it and see that swapping them in any sum will never change the result of the game. I mean, all you have to show is that in any winning strategy, you will do it more like this one. That clearly makes it so that they add. This is useless. Okay. So this hints at, if we remember the special motivating example of the Sapinho game, there was this position. Let's use first this one as an example. How was this position? Let's call this one G, this game. How does this one look in the abstract notation? So left can move to another position, so we will not need to do some auxiliary analysis here. Left can move to this position, but this one is equivalent to 0. I'm not sure if you see this yet, but this is actually an idea that already happens in impartial games. If you have a game where whoever plays loses, right? The game is such that the second player always has winning strategy. Even here with partisan games, I mean, it's not like left always wins, right always wins. It's whoever wins, whoever plays loses. If I play this game alone by itself, well, that game will always be equivalent to this. This is something nice of the general theory that still holds. Like the positions that by themselves are whoever plays loses still are exactly the position that can be erased in a sum of games and have no effect. And there is a strategical proof of that. Why can you erase them without affecting the result? Well, ignore it and do your strategy as if that did not exist. If you did have a winning strategy, that strategy will never call you to play here because you are ignoring it, and you will not run out of moves because you are assuming that you have a winning strategy. So your opponent is the one that at some point will need to play here, even if they wait as long as possible. Well, when this is the only thing that remains, but at some point they will have to play here. And whenever they play here, you just respond with your winning strategy here as the second player and keep doing that. Right? So you play in parallel your winning strategy for the rest of the game and your specific winning strategy as the second player here, because here you will be the second player. You are never forced to move there, so when your opponent moves, you respond as a second player and keep doing it. Is that more or less understandable? That is the constructive argument of how would the strategy look that justifies that erasing this in any sum of games it will not change the result. So this actually behaves. It is not a real theory, there are moves there. But for strategic purposes, if you play well, this can be ignored. It will never change the result of a game. So we say that it is equivalent to 0. So in that, by noticing that and noticing that if it is to the left, it is the same situation. I mean, why this one is a 0? Well, if left starts, they cannot move, they lost. If right, so second player is win. If right starts, because now this will depend on that. If right starts, they can only jump here, but then left responds with a jump over there, like this and this. And now they cannot move anymore, so again, the one who started loses, cannot move. Right? So it is an actual losing position for whoever is playing, so it behaves as a 0. So with that in mind, both players can move only to that position, to the 0 position. So this is a game where both players have the same option, and that option is already an impartial game, so this is an impartial game in the end, so this has to be equivalent to some nim heap. And this is actually the single nim heap, right? You're only moving to destroy the position. That is exactly the single nim heap, right? So this justifies what I have mentioned before, right? This position actually behaves like a single nim heap, right? But what is more surprising is that if I added one extra space over there, right, then things get more complicated, and this ended up behaving as 1/2, basically. Right? The reason is that if you have 2 copies of this, it becomes something that behaves exactly identical for the sum as having just the normal number 1. That I am not proving right now, but there will be ways to prove that. I might mention that quickly tomorrow. But where, if you want to compute this, where does this 1/2 come from? Well, the rule is somewhat crazy, and the full proof is very involved. Like, you can read the full proof in the books, right? It's not long, but it's somewhat tedious. But the rules end up being not that complicated. It's more crazy than complicated what the rule is. In a game like this, if you analyze it, you will have a situation where left can move to a 0, and right can move to a 1. So, anytime, this is how numbers look, right? Star is not a number, because the left position and the right position are the same, so it is not clear that you are hurting your position if you play. But when you have numbers, and I mean real numbers basically, they will be even rational in our case, and more specific. If you have numbers on the left, numbers on the right, and all the numbers on the left are lower than all the numbers on the right, well, each player would prefer that the other one plays, right? In that sense, playing hurts your position. If left plays, he gets no move left, but if right plays, left has one more move. So each player is better if the other one is the one who moves, right? That is what defines a number. So games that have that property are much more treatable because we have a rule of how to put a number into them, and they don't have crazy behavior. So this would be a number. Again, a number would be any game where your left options are already numbers, so it's a recursive definition. Your right moves are already numbers, and every left option is lower than every right option, right? So this would not be a number. Left can move to 1 and right can move to -1. This is not a number, right? Not in the floating point sense, in the theory sense. Number. But 0, 1 is a number, right? And this should be a positive number because this is an advantage to left. If left starts, they play to 0 and win, right? No move for left. But if right starts, they are forced to move to 1. So left has one move, they do it, and they win. So no matter who starts, left wins. So this is not a 0. This behaves more like a positive number. But you can check that if you add in parallel a -1, now right will always win, right?
who can do it sort of by brute force. If right starts, they can just play to 1, and you have 1 minus 1, 0, but it is left turn, they will run out of moves. If, however, left start, they don't have moves here, so they are forced to move to 0, and then they have the minus 1, so right wins. So right wins always this combination. So this seems to be less of an advantage than a single 1. With a single 1 move advantage, left would have won when right started. But here, right is always good. So this ends up being a half. And you might guess that the rule is that the number that is right in between is the correct one. And that is not the rule, but it is close to the rule, right? I will just state the rule. But this is one of the most important treatable cases, right? That of numbers. Right? This one is not a number, by the way, because it is very. Players want to play here. They want to rush to play here, right? If left wins, plays here, they will have done a move and then have another one extra. But if right plays here first, they will have done a move and then they still have one more extra that the other one doesn't, right? It's like this is fighting for the right of one extra move. And if these numbers are bigger, this is like even more urgent. Like whoever plays first there gains like 10 extra moves, right? Which, if it was the other way around, minus 10 and 1, let's say, well, here it is a number because moving is worse. Each one prefers the other one. And what number do you think this is? Minus what?
9.
No. No.
Minus 9.
No. Very, very far away. It is actually 0. Whoever plays loses. So it has to be 0. Right? If left plays, they are giving 10 moves to the opponent, that's completely lost position. If right starts and they play their only move, they give 1 move to the opponent responds, they lose. So whoever plays loses. We already know that any move that whoever plays losing can be ignored. You have a global strategy as a 0. So this is a 0. And this argument will hold for any x, y, where x is negative and y is positive. Well, any game like that is a 0. Right? So the rule is more complicated than just the average. What is the actual rule? Well, there are different ways to think of them, but it is called the simplicity rule. There's a simpler version of the simplicity rule. I will state the simpler version. For finite games, which are the only ones that we are dealing with, right, this Dolophy theory can be used for infinite games, and it's more complicated, but we only care about finite games, I think, usually, hopefully. So if the games are finite, the denominators that will appear are powers of 2. Very, very nice property. Right? For infinite games, you get all the reals, but for finite games, as we usually have, any game that will appear will have the form like, I don't know, some numerator, and the denominator is always some power of 2, right? Positive or negative or 0. And the rule is like this. There is a criterion of how simple a number is, right? Integers are ranked by their absolute value. So 0 is the simplest number that there is. Then you have 1 and minus 1. Then you have 2 and minus 2. Well, I don't know why. 2 and minus 2, and so on. So all the integers are the simplest, and the closer they are to 0, the simpler they are. And then come all the numbers, the numbers, the rationals that have a denominator 2. Those are more complicated. So they are not integers. Right? Then come all of the numbers that have denominator 4. So of course, 2/4 is the same as 1/2, right? So this one will have the and so on. So this allows you to rank any fraction with denominator power of 2. And the rule happens to be that if you know that you have a number, so you have already identified your options and they are numbered, both left and right, so you take the maximum of the left ones, you take the minimum of the right ones because the other ones will be dominated, and now you know that you have to be between those two numbers, And the rule is, it's called the simplicity rule. The value of the game is the simplest number that fits inside that game. It's very crazy, but that is the rule. There are different equivalent games to state this rule, but this is the simplest way to state the simplicity. I will not prove it, but this allows us to solve many games. I mean, any game where all of its positions are numbers. So again, any game that has the property that moving always hurts your position and you're getting worse, which for example for Sapinios is almost the case, but not always because you have the star, and the star is not a number. Like, you sometimes get a better situation by moving in the star than the original. It's like non-comparable. It's not a total order. Among games, you don't have a total order that left always prefers something. Sometimes you cannot eliminate all the dominated options. But among numbers, you have, like, numbers are nice, are good things, like numbers we are used to, and numbers are totally ordered. So it's very nice. If you know that all your positions are numbers, you will always be able to choose, okay, the biggest one from the left, the smallest one from the right. If one of those happens to be empty, then it's as if it was an infinity. Right? If, for example, you have the game 3-0, well, as before, this is 4, right? I can move to a position with value 3. For the simplest value that is larger than 3. Those integers are the simplest ones. And if this would be that my interval is 3 up to infinity, because there's no restriction on the right, and the simplest thing that lives there is 4. So it satisfies the simplicity rule. The empty game is a very special case of, okay, the interval of allowed things would be the full line, and the simplest number is 0, so this has to be 0. So this allows us to solve as many games. I mean, I haven't stated it explicitly, but I hope you imagine that we call them this because this behaves well with the sum. That's the most surprising thing of all of this definition. If I happen to discover, okay, this game is 3/4, and the other one is -1/2, then if I am playing the sum of both games, that is equivalent to the 1/4, which is positive, so no matter who starts, left wins. Right? That is the general property. For positive numbers, left always wins, no matter who starts. For negative numbers, right always wins, no matter. For 0, whoever starts loses. Now, there are no numbers that have the property like the star, that whoever starts wins. Because in numbers, playing is bad, so it makes no sense. It cannot be good to have the move in a number. But in other things like the star, it can be good. Sometimes. It's like not comparable. Sometimes it is good to have the move, sometimes not. For numbers, everything is a bit simple. Not as simple probably as the impartial games, but simple. These are the most important cases. Then there are many more that we can add. But you already see that the theory gets much more complicated, right? So I have seen actual problems with values more complicated than numbers, like not much more complicated, but numbers and a few more things. I have seen that in actual context, but very few. Very few. So this is not the mainstream topic right now, which I think makes sense. It feels very niche, but I mean, Andrew already covered the important topics, so I told you I can now cover the non-important. Well, I hope you like this a little bit at least. The impartial sum of games, I mentioned, I recapped. I did a quick recap, and I think that one is critical because it's not like it appears a lot, but at some point it was very common. Now it has gone a bit out of fashion. But still, that one is much more common to see than the partisan game. Okay. And if you want to read much more about this, because this seems very interesting to you, like the best place is probably to read the winning ways for the mathematical place, right? But that will not be too useful for competitive programming, because I have seen very little problems. Unless it becomes very fashionable, I have seen, though, problems. It's not unseen, but it's very rare. Okay. Any question? Yes.
With
between the ones that have the denominator too. You also are by absolute value.
You don't, it's undefined because it doesn't matter. You have to think about it a bit why, but it won't be ambiguous. If you have ambiguity, there is a simpler one up. So I don't need to resolve this ambiguity. But yeah, that is not completely obvious. Like it would be simpler if I define a total order, but to make it simple, I intentionally did not define a total order, but it doesn't matter. If you have more than one value at some level that would fit, then for sure you have a simpler value that fits.
And how do you check if a number fits?
That is hard. That is not so easy. If the denominators are relatively small, which usually happens, but I've seen a hard problem with it. They are big. So you need like a sort of big integer, but in binary. It's an implicit big integer when you have like a fraction, basically, in the bit. But you would have to do sort of a binary search and calculate. You probably, if I'm not mistaken, you can start duplicating, right, and try with integers rounding, and if the integer interval is empty, the integer interval is not empty, which you can first compute by division, then you choose the closest to the interval. If that one is empty, you have like to refine your precision, which I think is duplicating the numbers and changing scale. And you can do that. You can keep duplicating until the interval becomes not empty, and it's like looking at the same level. It's similar to reading in base 2, but it's like the fractional part. So imagine you have the decimal point and the base 2. Well, it feels similar to. I mean, it depends on how you have this represented. You have more than one option. The actual binary representation is an option. Although it is quite tricky because for this, it's probably more convenient to have like a bit exotic base where you have ones and minus ones for the digits. So that way it is like centered, and I think that will help you with deciding what is the best option. But yes, exactly. Like if your values are very general, it's hard. The ideal case of this is that you only have a few values and you can do them by hand, and then you put them in the code. Like in the Sapinius one, you would be able to do all the analysis by hand, and the only value, the most complicated thing that appears is 1 half. So in my code, I put all the numbers duplicated, so they are integers, and I just do the calculation. But yes, a general example, the calculations is more complicated. Yes.
The denominators are always orders of 2.
Yes. That's I mean. None of this is obvious at this point. We will have to start proving things, but that can be proved. For finite games, we are only caring. If you have infinite games, I mean, it's the same, but the sets can be infinite. That is the intuition. You only need to ensure that there are no infinite descending chains, and then everything still makes sense. And this is akin. The numbers become akin to Dedekind tags. If you know what Dedekind tags are from analysis, like for example, root 2 suddenly appears when you move infinite games, because here you can put the set of all our fractions that we already have that are lower than root 2. So here we put all of the fractions that we already have that are bigger than root 2. I mean, only the powers of 2, but those are dense enough. And this game behaves exactly as root 2. You have infinite options, and if you need something that is only epsilon from root 2 smaller, you have it. If you want only epsilon bigger, you have it. So the actual behavior is exactly right. But of course, this is an infinite game, and so it's more complicated. Luckily, for finite games, yes, it stays in powers of 2, which allows this kind of representation. Any questions? Okay, this is clearly enough for today, so